This video is sponsored by Brilliant. More about them later. So according to the special theory of relativity, any object with mass cannot travel faster than light, at least in vacuum. Now, we humans have mass, and so there is absolutely no chance that we will ever be able to travel at the speed of light. At least as of the technology today, we cannot do that. And that's kind of sad because most of the effects described by the special theory of relativity only become observable or apparent to us only if we were able to travel at the speed of light or very close to the speed of light. Now, in this video, we'll try to simulate and see what the world around us would look like if we were able to travel at the speed of light or at least very close to it. To do this, we are going to use this physics simulator from MIT. The simulator is designed in form of a game to add a little bit of fun to it. This is how the interface looks like. Now, rather than trying to move at the speed of light, which is very huge, about 300 million meters per second, what happens here in the game is that as we collect these little objects called orbs, the speed of light gets slowed down to the extent that our walking speed at some point is going to be equal to that speed of light. In the interface, you can see right over here in the corner, you have two knobs. Down here is my walking speed, and on top is the speed of light. Now you will see later in the game that as I collect more and more orbs, the speed of light is going to get smaller and smaller, and my walking speed is going to remain constant actually in the game, but the speed of light is going to keep getting smaller, and at some point my walking speed can actually be equal to the speed of light. On the other corner, you also see the number of orbs that I've collected out of 100. The game has a total of 100 orbs. Down here, you also have this strip, which is the electromagnetic spectrum. And basically what this will do in the game is to show us the possible range of electromagnetic waves that become visible to us, especially as our speed gets close to the speed of light. So let's start collecting some orbs so that we lower the speed of light and hopefully see some of these interesting effects of relativity. Now you notice immediately as I start collecting the orbs, the environment around me starts to look different, especially as my speed increases. As I accelerate, you begin to see weird colors pop up and different variations in the brightness. Now I've collected about 15 orbs in the game so far, and something cool I want to show you here. Notice in the game how objects get brighter as I move towards them or as I approach them, and how they get darker as I move backwards. This is called the searchlight effect or relativistic aberration, and basically what happens here is that as I move towards an object, there is more photons that are hitting my eye per second. Therefore, I see more photons, more brightness, and as I move backwards, few photons are reaching my eyes per second, so the objects appear darker. Now this effect is going to become even more intense as I collect more orbs. Here's the footage of the same effect when I've collected more than 50 orbs. Notice again, as I move backwards, objects get darker, and as I move forward, objects become brighter. You can see the same effect when I try to move sideways. One side becomes brighter, the side that I'm moving towards, and the other side that I'm moving away from becomes darker. The second effect you might have noticed already in the game is the appearance of all these weird colors as I move relative to other objects. This effect is called Relativistic Doppler Effect. Doppler effect, simply stated, is the apparent change in the wavelength and frequency of waves when there is relative motion between the source of waves and the observer. This equation here describes relativistic Doppler effect in terms of wavelength. It basically tells us what happens to the observed wavelength as I move towards objects or as I move away from the objects. In this equation, c is the speed of light and v is the relative velocity between the source of waves and the observer. V is positive when the source of waves and the observer are moving away from each other, and it's negative when the source of waves and the observer are moving towards each other. And because V over C is a fraction in this equation, relativistic Doppler effect only becomes observable when the relative velocity between the source and the observer is very close to the speed of light. For example, if V is positive and let's say our value of V is very close to the speed of light, then the observed wavelength is obviously going to be greater than the original wavelength of the source. Now back to the game, observe that as I move towards an object, I see a blue color here. This is called a blue shift, and as I move away from the object, I see a red color, and this is what we call a red shift. This effect becomes more apparent and visible also when I move sideways rather than forward and backwards. Now let's try to move sideways to see the same effect. Now notice that the side that I'm moving towards becomes blue shifted, and the side that I'm moving away from becomes red shifted. And by the way, scientists use relativistic Doppler effect to know if an object is moving towards us or moving away from us. This is how we know that the universe is expanding, because all the galaxies and stars that we look at are red shifted, which means they are actually moving away from us. And this provides some pretty good evidence for the Big Bang theory. Another effect here is that as the speed of light slows down and our speed approaches the speed of light, our range of wavelengths that we can see becomes bigger. You can see that on the electromagnetic spectrum that is displayed down here in the game. We now have a bigger range of wavelengths and frequencies that our eyes can detect, and most of these are wavelengths and frequencies that we wouldn't normally detect. So as an example, all hot objects emit infrared radiations, but our eyes cannot see these because they are outside of the visible range. Now in this game we have huts that have chimneys on them, and let's assume that these chimneys are hot because that's what they are for anyway. So as I move relative to these chimneys, notice how they start to appear red, and what this means is that we can now see infrared, which we wouldn't normally see. So in summary, the faster we move in this game, the bigger our visible range becomes. The more wavelengths we can see, the more things that become visible to our eyes that under normal conditions shouldn't be visible to us. Now before moving on to the last two really interesting observations, let me tell you about Brilliant, the sponsor of this video. Learning can be fun and memorable when it's hands-on and interactive. Brilliant brings very abstract concepts such as relativity down to earth. Every idea is boiled down to its basic level to make it intuitive and as understandable as possible. With hundreds of simulations you can play with and interactive quizzes, you cannot go wrong with Brilliant. And if you're a procrastinator like me, Brilliant has just the right tools to keep you motivated and focused towards your learning goals. So if you want to learn science, math and computer science with great ease, Brilliant is for you. And if you're enjoying this video so far, you will definitely enjoy Brilliant's course on Special Relativity, which is one that I checked myself and learned a lot of cool stuff while I was preparing for this video. Brilliant was generous enough to give a 30-day free trial for viewers of this channel if you sign up using the special link brilliant.org/thephysicsmathwizard. I'll leave that link in the description also. The offer is available for the first 200 people to sign up using that link, and in case you wish to sign up for their premium subscription, you'll also get a 20% discount. So a big shout out to Brilliant for supporting the channel and sponsoring this video. Now back to special relativity. You might have heard that if an object travels very fast, close to the speed of light, then its time ticks slowly or its time runs slower. This effect is known as time dilation. Now while it's hard to see that in the game, one thing you notice is that as I collect more and more orbs, it appears as though my speed is increasing. It looks like I'm running faster, but that's not actually the case. In this game, my maximum speed remains constant. It's only the speed of light that is slowing down. So because my speed is approaching that of light, my time starts to run slower, and so I'm able to cover more space for the same amount of time, and thus I appear to be moving faster. Another related effect that's also very hard to see in the game here is the runtime effect. Now for you to see an object, light has to travel from that object to your eyes. For instance, as you're watching this video, light is traveling from your screen to your eyes, and so you're able to see the video. Light travels at an extremely fast speed, but even then, it takes some time for photons to travel from an object to our eyes. As an example, light from the sun takes about 8 minutes to reach Earth, even at this incredible speed. What this means is that if something happened at the sun, we wouldn't be able to know until 8 minutes elapse. Also, there are some objects in the universe whose light has taken millions of years to reach us. That's why, by the way, we can't tell how big the universe is, because probably there are some other objects outside the observable universe, except that light hasn't traveled from those objects to reach our eyes. Maybe they're just too far away that light from those objects has not been able to reach our eyes yet, or to be detected by our instruments. Back to the runtime effect, as our speed approaches the speed of light, photons are almost reaching our eyes instantaneously, meaning that there is no delay between when events occur and when light reaches our eyes. This is kind of creepy because it means we can look into the future and we basically see things as they are happening in real time, no matter how far they are from us. Now, one thing you also noticed in the game is that as we went further into the game, objects around us started to warp, especially as we move relative to them. This is a combination of the Lorentz transformation and another less known effect known as the Terrell effect. Now, this is kind of counterintuitive because from theory, we actually expect that as we move very fast towards the speed of light, objects are supposed to undergo length contraction. So as we move towards an object, we would basically expect it to become thinner or squashed together. But what we see is actually the opposite. Objects tend to get stretched and warped as we move relative to them. Again, it's not just length contraction at play here, it's a combination of Lorentz transformation and the Terrell effect. I'll leave some links in the description in case you want to read more about those. Thanks to this simulation that the designers paid great attention to such detail to make sure it comes out perfectly and as accurately as possible. And yes, that brings us to the end of this video. Thanks for watching. If you like it, give it a thumbs up. If there are some effects that maybe I didn't notice in the game and you noticed them, please write them in the comments. And if you want to support me and the channel to make more videos like this, please do subscribe. You can also support me on Patreon using the link in the description. Thanks again for watching this video. I'll see you in the next one. Bye.